So yesterday we finished up talking about acid catalyzed hydration. We said that it's really similar to hydrohalogenation, where you protonate first, and you always want to go through your most stable carbocation intermediate, which means you have to watch out for stereoisomers if you're forming a stereocenter. And we said in this case the acid's catalytic. It proceeds faster when you have a more substituted alkene. And we can favor addition reactions by running the reaction at a colder temperature and by adding in a lot of water. So normally when we do addition reactions, we run the acid very dilute. So I'm going to give us a challenge warm-up problem. Oh. Whoa. And I want you guys to try to figure out the mechanism for this. I'll give you the product though. And we've got catalytic acid, so I'll put H plus in brackets. And this will be dilute. And our final product is actually a ring with two methyl groups coming off of it. So I want you to try to rationalize the mechanism for this acid catalyzed hydration reaction. That's a big sigh. Give you guys a hint too if you're stuck. What's the fastest reaction in chemistry? Acid. Acid base. What are we going to protonate? Our alcohol. The alcohol is the most basic site on this molecule. So the first step, before you do anything else, is to protonate this alcohol. So now we've got our hydronium-like reagent. What do you think will happen next? If it falls off, we'd form a primary carbocation. It's not super likely. Yeah, the double bond can attack the hydronium and steal one of those protons. All right, so we're moving along. Where should the carbocation be? What do you guys think? Oops. Yeah, the most substituted carbon. So we'd end up with our tertiary carbocation on this internal carbon there. What do you think will happen next? Yeah, in this case, our alcohol with its lone pair can add in, so we don't need a water molecule necessarily, we just need some sort of alcohol. Alright, so we're almost there. What's the last step? Yeah, we just need another equivalent of our alcohol or some sort of base to deprotonate this. So I'll just write minus H plus. And we can form our cyclized product. So a lot of these mechanisms won't necessarily look exactly like the practice mechanisms we cover, but just work through them step by step and try to break them down into their elementary parts. Another thing too, one big piece of advice I always got from my advisor was number your carbons and the members of your ring in order to keep track of things. So here we've got 1, 2, 3, 4, 5, 6. That means we're going to form a 6-membered ring. And you can go through and say 1, 2, 3, 4, 5, 6. And in that 6th position, we have 2 methyl groups coming off. So if you are having trouble keeping track of things, it's always a good idea to number them.
Is that minus H?
Yeah, so that's just shorthand for deprotonation.
So why write a false negative?
Because we do need to indicate that it's a distinct intermediate that is formed. Yep, Ramon.
Oh, wait, never mind.
All right. So let's continue on. And we're going to change gears a little bit to a different type of reaction along the same lines. And this new reaction was formed because there's a problem when we do acid catalyzed hydration. So let's go over the problem. Let's say we've got water and this acid, and or this alkene, and we're going to use dilute acid. What will our product be? You don't have to provide the full mechanism unless you really want the practice, but what do you think the product will be?
Alcohol.
It'll be an alcohol. Why did the product have the alcohol come off of that carbon? Rearrangement, right? So in the first step, we would form a secondary carbocation that could undergo rearrangement to that tertiary carbocation. And so the product is the result of a carbocation rearrangement. But let's say I'm a chemist and I say I really don't want the alcohol there. I want the alcohol coming off of that carbon. I don't want it to undergo a rearrangement. Then we're stuck. Using acid catalyzed hydration, we can't get an alcohol installed in that position. However, there's a trick. So let's go over the trick. And the trick is to use mercuric acetate. Yeah, exactly. I'm sure everybody was thinking that, like, oh, why didn't I think of mercuric acetate? Step 1. Mercuric acetate looks like this. It's got 2 acetate groups covalently bound to mercury. Not the most environmentally friendly reagent, so it's not the preferred route, but it is the only route available if you're worried about rearrangements. Oftentimes people will shorthand this and they'll write HG OAC in brackets and then a subscript 2. These groups are called acetate groups, and so quite frequently you'll see organic chemists just abbreviate them as OAC. Sorry, the acetate group is the outer portion. There we go. Which part? HG. Sorry, my handwriting is not the best on the tablets.
Is that MERCU or MU?
I think it's ME. Sorry. There we go. Mercuric acetate. All right, the first step for this reaction is a heterolytic bond cleavage, where the sigma bond will dump its electrons directly onto the oxygen on one of the acetates. And this is an equilibrium reaction, so not a lot of it's present in solution, but enough of it is. And what charge should we have on our mercury now? What do you guys think? Positive. We took electrons away. So now we've got mercury with a positive charge. Is that a good nucleophile or electrophile? It's a good electrophile. So step 2 involves a nucleophilic attack on that electrophile. So let's say we've got this alkene, and we've got our intermediate that we just formed. And I'm going to use the OAC abbreviation just to save some time. Whoops. And the mercury is positive. Our pi bond can act as a nucleophile and attack that mercury. All right, we know the carbocation wants to be on the most stable position, so it'll form on that tertiary carbon. And then we now have a new organometallic bond to mercury. However, mercury is really big. It likes to share its electron density. So what do you think that lone pair might do? Yeah, exactly. So what ends up happening in this case is a lone pair on mercury will donate those electrons into the positive center. And you end up forming a mercurinium ion. There we go.
And is that still similar where it can only happen like up to 2 carbons away?
Yes, it can only occur at the adjacent carbon, but the nice thing with an addition reaction is the carbocation is always going to be adjacent to that mercury. So in this case, the mercury will always hop over and form this mercurinium ion. So in the previous step, we had a carbocation adjacent to this lone pair. So this lone pair is really attracted to that positive center, and we'll end up forming this mercurinium ion in solution.
So there's another line right there.
Yep, so now we've got a 3-membered ring, covalent bond here, and covalent bond there. All right, the next step involves ring opening.
How did we get that propene? Like, do we put it in a solution? Or?
So in this case, the mercury is so attracted to that positive center, it will overcome the ring strain and actually favor forming a 3-membered ring. It's a little bit unusual, and we'll see this again with bromination reactions as well. All right, step 3. Now that we've got our mercurinium ion, it's somewhat unstable due to the ring strain. And I'm going to draw these as dashes and wedges just to show some perspective. Now if we have an alcohol like water, I'm going to draw this as just OH2 with 2 lone pairs. This alcohol is going to end up attacking the underside of this mercurinium ion. Which side do you think it's more likely to attack? There's 2 possible explanations. Sterically, which side's more accessible, the right or the left? The right side's more accessible by sterics, but what's the other thing we have to look at? So is the dual-edged sword sterics and electronics, right? So we have to look at which one will undergo the most stable transition state. So if we think about this, water will most likely attack the left-hand side, because when we think about it, this left-hand carbon has a lot of positive character on there. So in this case, even though sterics indicate that the water should attack the less substituted side, electronics says that the water will attack the more substituted side. So when we do this, it's going to slingshot this mercury out, and we end up forming some new bonds. And we've got OH2 added in. The oxygen has a positive charge. And then we've got HGOAC. And we still have this methyl group. Looks complicated, I know. The last step is you just need a little bit of base to do a deprotonation. And we lose that proton coming off of the water. So this is the 3 steps required for a mercuration reaction. The next thing we're going to do is take this product that we formed and pop off that mercury. So we've got this intermediate that we just showed. We're going to use a new reagent that we're going to see a lot in the future. NaBH4. This is sodium borohydride. It's a really, really nice reducing agent. And when we do this, we just pop off that mercury. And we get our alcohol. So this is going to be our final product. No rearrangements occurred. Yep.
What causes the mercury to leave all of a sudden?
We're not going to get into the mechanism of that, but sodium borohydride is a nice hydride source. So what's hydride? Do you remember what that is? Yeah, it's H-. So in this case, the H- doesn't act as a true nucleophile. It's acting as both more of a reducing agent, and when we reduce off that mercury, we can replace it with a hydrogen. Yeah, the mechanisms for these reactions, once in a while I'll tell you guys not to worry about them. This is one of those reactions where I'm not super concerned with you knowing the mechanism of the reduction step. Yep.
So what's the difference between a normal hydrogen ion and a hydrogen that you draw there? You got a little dash there, also with a positive charge.
Are you talking about right here?
Yeah.
So oftentimes, especially second term, just to save time, instead of showing individual protonations and deprotonations with arrows, I'll just write plus H plus or minus H plus to show protons being gained or lost. Does that make sense?
So what is that mechanism? Is it loss?
It just means loss of a proton. So for example, we lost this proton down here. So minus H plus just indicates a deprotonation event.
Okay.
All right.
Professor Abel?
Yep.
I just wanted to know why you chose to take off the HG part. Like, is it just because that's the product you chose, or is there like a reason?
So are you saying why did we lose this part down here?
Yeah, like is it just because you were trying to make that product?
Yes, exactly. So the chemists that developed this reaction purposely wanted to make a reaction that resulted in the oxygen getting added into the position that didn't undergo rearrangement at all. And the only way they were able to do this was to do it through a mercuration reduction reaction. So the first step is adding in that mercury and forming your mercuranium ion. Then you do a SN2 style attack, ring open it, and then you have to get rid of that mercury in the end to get to your final alcohol product. It's kind of roundabout, I know, but it's one of the only solutions available to that problem. All right. Now we've got another kind of crazy looking reaction.
Okay.
Yep.
So could you explain why, where the red arrows are, why it favors the more sterically hindered side?
It's because the lone pair is going to be most attracted to the oxygen with more positive character. And so that carbon on the left has a lot more positive character on it from the formation of the mercuranium ion. That's a much, much weaker bond right here, and so it's the most readily broken bond. Does that make sense? We're going to cover this a lot more too when we get into the chapter on epoxides as well, because there are some situations where sterics matter more than electronics. But for oxymercuration reactions, you're always going to go after the more substituted side of the mercurium ion. Yep.
Do you have cases where there's no difference between the two sides?
Yeah, if it's a tie, it'll result in a mixture. Good question. All right, the next reaction we're going to look at is hydroboration oxidation. And hydroboration oxidation's a kind of neat reaction. So if you recall, we have now a couple different ways to form alcohols. But in both of these examples, it would result in an alcohol coming off of our more substituted side. What was the first way we could get an alcohol from this alkene? Do we need concentrated acid, dilute acid? What would work? Heard somebody say it. Dilute acid. So dilute acid and water would work for this top reaction, and we just discovered a new way of getting this reaction to work that avoids rearrangements, where we use mercuric acetate followed by sodium borohydride. For this specific starting material, they give the exact same product. However, what if we don't want the alcohol to get attached to that carbon? What if we want it to be attached to the other carbon on the alkene? Go up. Is that high enough?
Yeah.
Okay. So in this example, we added the alcohol onto the more substituted side of the alkene. But what if we want to add it to the less substituted side of the alkene? What would this product be called? Would it be Markovnikov, anti-Markovnikov? Anti-Markovnikov. Both of these were Markovnikov.
Because they're more substituted, right?
Exactly. But there are some situations where we might need to get the anti-Markovnikov product.
You said you had to use peroxide.
That was with HBr, right? So when we were doing hydrohalogenation, we could do it just simply by adding in some peroxide impurities, but this time we're trying to get an alcohol installed, not a halogen. So we've got to be a little bit creative here. So let's write this down. The reagents we're going to use for this are borane, which is BH3, and then it gets complex with THF. So we just write BH3.THF. Does anybody remember what THF stands for? Tetrahydrofuran. It's an ether solvent that looks like this. It's got 2 lone pairs on there. Why might THF like to complex borane? Yeah, the p orbital, right? If we think about borane, I'll scroll up, has this empty p orbital sticking up and down right there. So this lone pair from THF will just occupy that p orbital and form a Lewis acid-base adduct. So BH3.THF is really just a fancy way of using borane. All right, the next reagent we're going to use, we have to indicate it by putting the second step in, is going to be hydrogen peroxide and sodium hydroxide. If we use both of these reagents in the correct order, we can get hydration at the less substituted side of the alkene. I'm going to erase this really quick. And let's talk a little bit about the regiochemistry before I discuss the mechanism. So let's take an example. I'm going to use this alkene. And we've got borane, and I'm just going to show it as regular borane, not complexed. What will end up happening is something a little bit bizarre, but this boron will end up being attacked by the pi bond. And in this case, the boron will want to be attached onto the less substituted side of the alkene. Why wouldn't the boron get attached to the more substituted side? I heard somebody say it in the back quietly. It's not electronics, it's sterics. So in this case, boron can more readily approach that top carbon, not the bottom carbon. And then when this happens, a hydride gets transferred over to the lower carbon. So we get this kind of funky looking transition state where we've got a hydride getting handed off to that bottom carbon. We're breaking a bond to this boron, and then this boron's forming a bond to that top carbon, and then we've got two hydrogens coming off. And when you're done, you now have new hydrogen coming off that bottom carbon. And let me clean this up a little bit, sorry. And you've got BH2 coming off there. Oh. I have good news for you guys though. The rest of this mechanism is super tedious and long, and I'm not going to require that you guys know it. I just want you to know the regiochemistry. If you are interested in watching the full mechanism video, I've got a link to the Khan Academy here where they go through step by step, but it's one of the steppiest mechanisms you'll see in organic chemistry series, and honestly I don't think it's worth our time. The biggest thing I want you to take away from hydroboration oxidation is that when you do this, the BH3 right here is going to get replaced by an OH in the end. So your alcohol is always going to form on your less substituted side of your alkene. It should be BH2 here, sorry. But when is all said and done, this will be swapped out with an OH. So watch full mechanism online if you want. All right.
Professor?
Yep.
So I know from the halogenation that if you have something like chlorine or bromine, it will still attack the less substituted side? No.
The more substituted.
The more substituted side. Yeah, right. The more substituted side. But chlorine is bigger than bromine or than boron. So why is it sterically hindered, whereas like a bigger molecule isn't?
So in hydroboration oxidation, in hydrohalogenation, it's a two-step reaction, right? First step is forming your carbocation, and then your nucleophile adds in. This goes straight to your alkyl borane in one step, meaning no intermediates are formed. So in that case, sterics matters a lot more. Again, it's getting back to that duality of sometimes we're looking at electronics, meaning are we forming the most stable intermediate or going through the most stable transition state? Other times we look at sterics and we say how accessible is the approach? Yeah, it's a little bit tricky with this one, but like I said, don't get too hung up on the mechanism. Just remember that hydroboration oxidation gives you your anti-Markovnikov product for a hydration reaction. All right, we've got to talk a little bit about stereochemistry, though. Yep. Yes, with hydroboration oxidation, it will always give you the anti-Markovnikov product. If we want the Markovnikov product, we can use dilute acid or the Oxymercuration, Demercuration. However, with anti-Markovnikov, this is the only route we have to get there.
So it's more based on the reagents.
Exactly. Yeah, what we're going to do this term is we're going to build our synthetic toolbox. So we're going to discover a variety of different ways to make similar molecules, and sometimes we want specific regiochemistry or stereochemistry, and that's going to determine which reagents we use. All right. There's unique stereochemistry with this reaction that involves the syn addition of hydrogen and your alcohol. So let's take an example of this. Let's say we've got this alkene, so it's a cyclohexene, and I'm going to react this with our borane THF complex. Whoops. And I'm going to follow this up with hydrogen peroxide and sodium hydroxide. Which carbon do you think is going to be attacked? The one in blue or the one in green on the bottom? Yeah, the less substituted side. So the alcohol is going to get added to that green carbon because that's the anti-Markovnikov position. But we also have to account for the hydrogen that's added in. Oops, sorry. Shoot, there it goes. All right. If we do this, the hydrogen is always going to be added in the same side of the ring or same side of the alkene as your alcohol. So in this case, if we look at this hydrogen's a wedge. That means this alcohol is also going to be a wedge. Do you think we might get another product out of this? What do you guys think? Yeah, the enantiomer. The reality is the borane could attack from either face of that alkene, so you'll get a mixture of products out of this. Specifically, you'll get a mixture of enantiomers. But in each case, you notice how the alcohol is on the same side of the alkene as the hydrogen that was added in. You always have to keep track of that. So in this case, you're going to observe a mixture of enantiomers. Syn just means it's going to be on the same side. Anti means it's going to be on opposite sides. Yep?
Is the reason that we chose the less substituted side to be attacked because of the BH3 THF?
Exactly. If we did this using dilute acid, it would add to that blue carbon. But because we use these special conditions, we're going to observe anti-Markovnikov products.
Why do you only see syn addition?
It has to do with the overall mechanism of the reaction, which, like I said, is really steppy. If you're interested in it, you can watch the video in more detail, or we can talk about it in my office. Yep.
Can we use the dilute H on this?
No, in this case, if we use dilute acid, it would add the alcohol onto that blue carbon. We want it to get added onto that green carbon.
Okay.
Yeah. All right, I'll show you guys a nice trick with this. Trick is when peroxides are used, think of anti-Markovnikov addition. So in this example, we had peroxides here, so we knew it was going to add into that green carbon. If we see hydrohalogenation with peroxides, same thing. We've got to think of anti-Markovnikov addition. Does that make sense? All right, so we're going to switch gears a little bit away from alcohols, and we're going to go into a reaction we actually saw last term a little bit. And this is plain old halogenation. Do what? To the last page? Okay, let me pull back. Oop.
Is it for C1?
When peroxides are seen, think of anti-Markovnikov addition. So if you see H2O2 or 8ROOR, you should always think of anti-Markovnikov. All right, so let's go to halogenation. Halogenation reactions are pretty common. Oop. And in this case, we're not going to use HBr. I'm going to use Br2, which is elemental bromine. And this will be our electrophile. And our pi bond, just as in the other examples, is going to act as our nucleophile. So in this case, our nucleophile is going to attack our electrophile and kick off one of the bromines. This is a weird example of an electrophile that's due to an instantaneous dipole. There's not a net dipole in Br2, but there's an instantaneous dipole so that the pi bond can attack the bromine and kick off bromide. The product for this reaction, again, involves a three-membered ring. And this bromine now has a positive charge. And we end up with Br minus. This is called a bromonium ion. It does, but the nice thing is, because it's so unstable, what do you think might happen?
Spontaneous reaction?
Yeah, it'll happen really quick. This Br minus will attack from the underneath side of one of these carbons, just like we saw in the oxymercuration reaction, and slingshot this molecule open.
So is it hitting the carbon, the negative bromine?
Yeah, the bromide is going from the underneath, and it's going to end up attacking one of these carbons. In this case, does it matter which carbon's being attacked? No, they're equivalent, so there's really no preference for this. And for bromination reactions in general, we're not overly concerned about it. We do need to draw that bromonium ion intermediate, though, because we know it goes through that intermediate. It doesn't go through a carbocation intermediate. So our final product from this reaction has bromines that are added to opposite faces of that original alkene. So if we look at this, we could say, all right, this bromine's on opposite sides of the alkene as that bromine, so we refer to this as anti-addition. So in this addition reaction, we're not observing syn addition of two substituents coming off of an alkene. We're observing anti-addition, where they're coming off of opposite faces. The other cool thing with this reaction is that it will sometimes work with chlorine. But we really don't ever observe it with fluorine or iodine. It's just simply too unstable and too unreactive for both of those cases. You'll usually see it with bromine in the textbook, and that's primarily how I use it. So let's take an example of this reaction and work through the mechanism in more detail. And I'm going to use abbreviations. I'm going to use ME for methyl, ET for ethyl, ME here, and H here. So this is our alkene, and we're going to brominate it. All right. What do you guys think will happen first? Yeah, we're going to have our pi bond attack the bromine. And we're going to kick off our bromide. So now when we do this, let me clean this up a little. We're going to get a new bromonium. And in this case, our methyl groups are going to be on the same side because they were originally on the same side of the alkene. So I'm going to draw those both with wedges. And then our ethyl group over here is going to be in the back. And our hydrogen is also going to be in the back. So we've got our bromonium ion. However, there's also the possibility of this doing an attack from the bottom side of that alkene, right? Because if we think about a pi bond, there's a p lobe sticking up above that double bond and one down below, so either side could attack. So let's consider the alternate product. Again, the methyl groups are going to remain on the same side. But in this case, our hydrogen's sticking back, and in this one, our ethyl group's sticking back. And there we go. What's the relationship between these two intermediates? Are they identical diastereomers and enantiomers? This becomes kind of tricky. If we try to overlay these, can we? No. But they're mirror images of one another, right? So what would the relationship be? Enantiomers. So we get two different possible enantiomers. As intermediates, and we've got bromide in each case. So in this case, the bromide can add into one of these carbons, slingshot it open, or in this case, it could attack this carbon and slingshot it open. So let's look at both potential products. We've got anti-addition of bromines. We've got our methyl group still in that same position. This hydrogen going back. This methyl group coming back. And this ethyl group here. And then for this one, we still have anti-addition, but we're going to form the enantiomer of the product. And a hydrogen. So it forms a mixture of enantiomers.
The methyls are still going out, right?
The methyl groups are going to be on the same side for all of these. So you notice how they're wedges, both of them on the right molecule and on the left molecule. But if we tried to name these, we would notice that the stereochemistry was flipped for all of the positions. Yep?
Why didn't we use, why didn't the BR attack on the other side?
Why didn't it attack on the side with the methyl group and the hydrogen? In that case, that carbon's going to be a little less reactive because when you break that bond, it goes through a partial positive. And so the bromide tends to attack the more substituted side because it's the most stable with a partial positive charge. In this case, it doesn't really matter too much. You'll still get to the same products, but we'll cover that a lot more when we get to epoxides.
This is a racemic.
Yes, it'll be a racemic mixture. So for your problem of the day that I handed out, the key thing I want you guys to do is to draw the top side attack and bottom side attack of BR2 and determine whether or not the products you get out, if they're the same or if they're different. And I want you to try to go through and name all of those products as well. So you'll have to practice designating things as R or S. All right. I think we'll cut it off today. I want you guys to work on the problem of the day. Remember that the problem of the day should be worked on in groups. If you guys want, you can come talk to me. But ideally, I really want you guys to solve these as teams So try to rely on one another rather than just coming to my office and trying to get the answer out of me. All right? Boo.